Welcome back, students. In this lecture we will discuss about unstable or deficient structures. Okay, this is something to be discussed along with the determinacy of the structure. Okay. So as the name suggests, a structure is said to be unstable if it undergoes a rigid body movement upon the application of a small amount of force. It means that the structure cannot stand by itself. Okay, so this is mainly because of lack of sufficient number of internal or external constraints. Constraints means restrictions or reactions. Okay, so in order to ensure stability, a structure must have enough number of support reaction as well as the proper arrangement of members. Okay, so the overall stability of a structure can be divided into two types: external stability and internal stability. Okay, so a structure is said to be externally stable if there is no rigid body movement of the structure as a whole. Okay, and the structure is said to be internally stable if there is no rigid relative movement of one part of the structure with the other part. Okay, so it basically relates with defining the geometry, preserving the geometry of the structure. Okay, now let's see in details external stability in the cases in which the external instability will occur. Okay, so structure will be externally unstable if the reactive forces are less than the number of equilibrium. This is the case where the external static indeterminacy becomes negative. If the number of reaction is more than the number of available equation, it results in external stability. Here we have two reactions here and one reaction here. Okay, so total m is equal to 3 and number of equation is 3 equation plus an additional equation due to hinge, which means that number of reactions are 3 and 3 equations of equilibrium and additional equation due to hinge. This results in ds is equal to -1. Okay, in this case if you notice there are one reaction here, roller support, and two reaction here. However, we can find two additional hinges here, or this can be called as a link. Okay, so here also the total number of equation is 3 plus 1 plus 1, which is 5. So 5 equation and 3 reactions, which means that indeterminacy is -2. Okay, also you can observe here, if you apply a horizontal force or inclined force, something like this, you can notice that this AB member is free to move along the roller in horizontal direction. So in that case the structure is unstable. Okay, another condition is that all the reactions should not be parallel. If so, if all the reactions are parallel to each other, it will result in a linear instability. For example, you have 3 roller supports and each of the roller support is having one vertical reaction. Okay, so in this case if you apply a horizontal or inclined force, the structure is free to move along the roller. This means that this is a unstable case. Okay, next condition is that all the reactions should not be linearly concurrent, which means that all the reaction forces should not meet at a single point. So in this case, if you see RA, RB and RC, all the reactions are meeting at a single point O, which means that about O, when a force is applied on this beam, the beam will rotate about the point O. So this causes a rotational instability. Okay, same as in this case, it's a curved beam lying in the curved support. Okay, each support is a roller. Okay, so roller gives only reaction perpendicular to the surface. So all the reactions are meeting at a single point O, So if you apply a horizontal force, the entire beam will rotate about it will rotate like clockwise rotation, right? This is another case. Here also reaction forces are concurrent. Okay, so it will rotate when a external force is applied in this. Here is another truss example. This is a hinge, so the reaction is vertical reaction, horizontal reaction, and on the left side you can see a roller support, and it will apply reaction perpendicular to the roller, which means in this direction. So if you note that all the reaction forces are concurrent about this point, right? This force is directly coming onto this point, so all the reaction forces are concurrent at this point, which means that whenever external force is applied, the structure will rotate about this point. However, if you try like interchanging the support, okay, now you can see that only one reaction is here, a vertical reaction. In this case, we have only one vertical reaction at roller, and there are vertical and horizontal reaction at the hinge. So in this case, all the forces are not concurrent, okay, because this force is going somewhere else. So this is not a unstable structure. Now let's see what is internal instability. So the internal instability or geometric instability occurs mainly because of two reasons. One is condition of mechanism. So a mechanism is formed when there is a three collinear hinges. Okay. So in your beam, in nowhere there should be a possibility of three hinges continuously. In that case, that three hinges will form a mechanism there, which makes the structure unstable. Okay, so this is a mechanism. Three hinges are coming together, so the beam will rotate infinitely. Another one is there should be minimum number of members present in the structure. This is applicable mainly in case of trusses. So we have learned that for perfect trusses, m is equal to 2j minus 3. So if in a truss, in case of 2D trusses, so if in a truss, if the number of member is less than 2j minus 3, the structure is said to be deficient and unstable. Okay. Similarly, for a 3D truss, a perfect truss is m is equal to 3j minus 6. In a perfect truss, m is equal to 3j minus 6. So if in any 3D truss, if the number of member is less than 3j minus 6, then that structure is called as unstable structure or deficient structure. So let's see an example here. This is a two-dimensional truss. We have 1, 2, 3, 4, 5, 6, 7 members, and j is equal to 6. If you calculate 2j minus 3, 2j minus 3 is 9. Here number of members m, 7 is less than 9, so m is less than 2j minus 3, which means that the structure is geometrically unstable. So if you want to make this structure stable, you will have to provide two additional members also. So that's lack of members is the reason for stability here. So if you have to make this stable, you have to provide a member like this and add one more member from here to here. With this background, let's see one more example, a similar example, but here it's a cross bracing and here there is no bracing. Here if you calculate number of members, m is equal to 9 members are there and j is equal to 6. Here if you calculate 2j minus 3, it is 9, and again number of members is also 9, which means m is equal to 2j minus 3. So looking at this, it is a perfect truss. This should not be geometrically unstable. However, if you take the left portion only from here to here, number of members is 6, number of joint is 4, which means that 2j minus 3 will become 4. So here number of member is greater than 2j minus 3, which means that this particular left side is over stiff, and if you check the right side, m is equal to 4 and j is equal to 4. So if you calculate 2j minus 3 here, m is less than m4 is less than 2j minus 3, which is 5, which means the right side is deficient. So this causes a relative rigid body motion between one side to another. So which means that stress is geometrically unstable. That's it for today's lecture. We'll see more in coming lectures.